So here we have E equals to y minus y hat. Y hat, as we defined already in this example, this is a function of input x based on our theta, which is our parameter. So let me just replace it, y minus, instead of y hat, I'm gonna just write function of x based on our theta, which is w, and biases, which we can change. This is our theta. We are looking for minimizing the error. We want to minimize this error. I'm just gonna raise both sides by 2. E squared, let's say, equals to this one over y minus f of x based on our theta. I'm just showing it with theta so it would be shorter, raised by 2. All the changes, all the things that we can change here is just our parameter theta. The theta star is nothing but the arc of mean E squared. This is a value of optimized parameters. Let's take a look at this example one more time. In this example, we had only one input, therefore we had one output. But sometimes we just don't have only one input and there are more. Let me just show it with I of I, therefore the output would be y of I, and for this system yi hat. So meaning for each data we need to optimize the error and then find the best way to optimize the whole system for all the data. For example, in our patient and doctor system, let's say we have more than one patient, we have 1,000 patients. We should have I would be from 1 to 1,000. We have 1,000 samples, we have 1,000 data, therefore we need to show it with x of I and y of I. Let's back over there and just write it in another way. I'm gonna divide this part so I can continue here. The E of I, it can be patient number 2, patient number 55, equals to y of I minus y I hat. I just goes from 1 to n number of our samples. Here we are looking for minimizing the error, so mean of 1 over n, which is over the number of samples that we have, and I can just simply take the sum of n and I from 1. E square I. This is nothing but a mean square error. And this is not specifically for artificial neural network. We can also use this one for fuzzy systems. This is called MSE, or mean square error. Later, when we are working with MATLAB, we will see how important is this, and we will see how can we adjust the parameter to have this mean square error in the best way. This one was over y and this one was over y hat from the previous example. So later on MATLAB you will see if we have 1,000 data, they are in different positions, but we need to minimize the errors. We need to find a system to give the best option. It means minimizing the error, this distance, it should be minimized. We cannot really satisfy all the data for all the samples, but we can just minimize the error and see which line can fit better based on our data. We can already write a formula for the mean square error. We can show it with 1 over n, sum from I from 1 to n number of our samples that we have, and here inside the bracket we have y of I minus function of x of I based on our theta square. So this is a general formula for calculating mean square error, and as I mentioned, it's not only for artificial neural network. We can use this formula for different systems such as fuzzy systems. Whenever we're looking for optimization, we can just use this mean square error formula. Our goal in optimization is just to minimize the error. Using this mean square formula that we just calculated, we can simply achieve our goal. In this example, theta would be our weight and biases for our neural network. E of I is equal to y of I minus y hat of I. This y hat of I is the output of our neural network, and I can go from 1 to n. So let's just replace this part with E of I. Then we can see that why do we call it mean square error? Because this is just the minimum of a square of the error. We are looking for the methods of finding these coefficients of variations. In next session, we will talk about optimization methods to find these coefficients.